Chapter 5, Number 38. Suppose a rocket launches with an acceleration of 30.5 meters per second squared. What is the apparent weight of a 92 kilogram astronaut aboard this rocket? We will assume it accelerates upward, so we're going to draw a situation as usual. Here is the rocket, and in a way that does not really happen, here is the astronaut. And the rocket is, of course, accelerating upward. So there's thrust coming out, pushing it up, which means it goes up. And since the astronaut cannot go through the back of the rocket, the astronaut also goes up. So if we look at a free body diagram, we have astronaut, and the astronaut is being pulled upward or pushed upward by the bottom of the rocket. So there's a force pushing up, which I'll call the force of the rocket against his feet or back or however he's sitting. And then, of course, there's the Earth pulling the astronaut back because we're assuming it's launching from the Earth. All right, this would be different in deep space. And together they conspire to give us a net acceleration, an acceleration upward, which was given there as whatever, 30.5. So from the diagram, the net force on the astronaut in the y direction is the force of the rocket minus the force of gravity. The minus sign because gravity pulls us down, and we're taking upward to be plus y. And then from Newton's second law, we can say that the net force on the astronaut in the y direction has to be the mass of the astronaut times the acceleration in the y direction. And putting these two things together, we end up having Fr minus Fg equals MAy, which is just for us Ma. It's the force of the rocket against the astronaut that's going to be the apparent weight. This is going to be the thing we're actually looking for, because the astronaut can't feel the Earth on him. He doesn't feel his actual weight. Instead, he feels the force against him that stops him from falling. That's how we interpret as our weight. So we can just solve this over by saying, let's add Fg to both sides, and we're left with the force of the rocket against the person is going to be Fg plus Ma, which is m times g plus Ma, which I can factor to be m times g plus a, which you might remember from lecture notes where we talked about that's how we find the apparent weight. So not shockingly, we get the formula we had before. Now we just get some numbers. So we say it's a 92 kilogram astronaut times 9.81 meters per second squared plus the extraordinarily high acceleration of 30.5 or 3.5 g. And putting it all together, we get 3,700 newtons. Because we only have 2 digits, which is a little surprising for Walker, but we only have 2 digits here. If you carried the extra digit, it would have been 3,710 newtons. But there we go.